Could it be true that a city hundreds of miles away could drain an entire watershed? How did Los Angeles reach all the way into the Sierra Nevada to capture every drop of a once pristine valley's snowmelt and river flow? And what happened to the water, the lakes, and the ecosystems left behind? In the eastern Sierra, Owens Valley was a long, narrow basin carved by tectonics and filled by mountain water. Snowmelt and rain from the high peaks fed the Owens River and Owens Lake as a natural system. Then, in the early 1900s, engineers built a massive gravity-fed aqueduct that diverted those waters south to Los Angeles, leaving the valley almost empty. This story is not about politics or intrigue, but about geology and hydrology, how the lay of the land, rock and sediment made this giant water transfer possible, and what geologic processes ensued when the water was gone. Flanked by the Great Sierra Nevada on the west and the Inyo Mountains on the east, Owens Valley is a classic basin and range graben formed by normal faults. The valley floor is a trench between fault block mountains, filled with unconsolidated and semi-consolidated sediments from those mountains. Layer upon layer of alluvial fan debris, glacial moraine, stream deposits, and lake sediments blanket the basin. Interspersed in the valley fill are old volcanic lavas and ash from regional volcanoes in the Mono Inyo area. This thick pile of gravel, sand, silt, clay, and volcanic rock, known as valley fill, makes up the aquifer. Virtually all groundwater in Owens Valley flows through these sediments and is stored there. Beneath the sediments lies bedrock, ancient granite, metamorphic and sedimentary rocks of the Sierra and Inyo Mountains. But that bedrock beneath the valley floor is almost impermeable. In effect, Owens Valley is a natural basin built to hold water. Most water from rain and snow that does not evaporate ends up in the valley's sediment-poor space or in Owens Lake. Owens Valley is arid, averaging only about 15 centimetres, 6 inches of rain per year. But the real water wealth came from the adjacent Sierra Nevada. The high Sierra crest catches Pacific winter storms. On the west slope, precipitation is copious, dozens of inches per year, and much of it falls as snow at high elevation. In a wet winter, more than 10 metres, 30 to 40 feet, of snow can accumulate above 2,000 metres, 7,000 feet. The east side of the range is drier, but still receives on the order of 50 to 100 centimetres, 20 to 40 inches of snow and rain each year. When spring comes, this mountain snowpack melts and flows east into Owens Valley. Hundreds of tributary creeks and streams pour into the valley from the Sierra. In a normal year, almost all of that Sierra runoff drains into the Owens River system, which flows south along the valley. Under natural conditions before the aqueduct, most of that water eventually spread out into Owens Lake, a large saline lake at the valley's south end. Because the valley fill is permeable, water percolates downward from the streams and recharges the aquifer. The main water-bearing materials in the Owens Valley aquifer are gravel, sand, silt, and clay washed down from the surrounding mountains. Shallow groundwater, springs and seeps in the valley supported extensive wetlands and meadows around the lake. Geologists have determined that nearly all recharge to this groundwater comes from Sierra snowmelt and rain running into the valley. By contrast, only a tiny fraction of recharge comes from the Inyo Mountains, or direct rainfall on the valley floor. In other words, the Owens Valley aquifer depended almost entirely on water draining from the Sierra Nevada. This groundwater circulated slowly through the sand and gravel, supporting vegetation and seepages along the river, until ultimately it emptied into the Endohig Basin, Owens Lake, or was used by plants. In a nutshell, outside the lakebed itself, almost all of the valley's water supply, surface stream flow and groundwater, originated from the Sierra watershed and was held in or flowed through the thick alluvial valley fill. Since the aquifer was so crucial, it is no coincidence that Los Angeles set its sights on the Owens River. By 1913, engineers under William Mulholland built the Los Angeles Aqueduct to tap that Sierra water. The intake was at a concrete diversion weir on the Owens River high on the valley floor near the present-day Lone Pine area. This site sits roughly 750 meters, about 2,500 feet, above the San Fernando Valley's main reservoir at the foot of the Santa Susana Mountains. In other words, the Owens River intake is about a half-mile higher in elevation than the dam outlets near Los Angeles. That elevation difference made gravity the only power needed. From the start, no pumps were required. The aqueduct was laid out to keep the water constantly flowing downhill. Engineers carefully maintained a gentle slope, on the order of a few meters drop per kilometre, using canals, tunnels and pipes. In effect, the entire 370-kilometre, about 230-mile length from the Sierra to Los Angeles is one continuous gravity conduit. It is all achieved through careful grading and managing elevation along the way to keep the flow moving, noted one reviewer. In its upper reach, the aqueduct is an open canal, skirting the Owens River. The first 15 to 20 miles, about 24 to 32 kilometres, of canal run beside the river's channel, capturing snowmelt directly. About 32 kilometres, 20 miles, downstream from the diversion is a set of spill gates on the canal, the so-called Alabama Gates. These gates allow excess flow to be dumped back into the Owens River during flood conditions. They also serve as a maintenance outlet. Engineers chose this point to make a major design change. As the canal climbs the valley and leaves the natural alluvial channel, the risk of water loss to the sandy ground increases. Beyond the gates, the aqueduct channel is cut into the valley wall and no longer flush with the river bottom. To prevent seepage into the groundwater, the canal switches from earth-lined to a concrete-lined channel. This concrete lining dramatically reduces leakage into the ground, although evaporation from the exposed channel surface still occurs. In other words, below the Alabama Gates, the aqueduct was built as a seal conduit to keep the water above ground and flowing south. The aqueduct courses through Owens Valley from there, passing near the desiccated Owens Lake. Owens Lake, once a large saline lake several kilometres long, is now mostly dry. After the city began diverting virtually all of the Owens River water, the lake shrank rapidly. By 1926, it had completely dried up. Owens Lake's bed is now a broad, cracked playa, salt-crusted mudflats, punctuated by a small remnant brine pool and sporadic pools fed by local springs. In the dry lakebed, grey and white materials are exactly the exposed fine sediments and salt deposits that once lay underwater. Strong desert winds churn this fine clay and silt into dust. Geologic surveys and space observations confirm that as a result of the diversion, Owens Lake became a prodigious dust source. In fact, Owens Lake has been called the largest single source of airborne dust particulate matter, 10 pollution, in the United States. Once the water was rerouted, the lakebed's fine sediment was exposed. Scientists even gave its dust a name. The local Keeler fog describes the choking dust storms that blew out of Owens Lake onto nearby towns and into the atmosphere. The silts were left by long-ago glacial and river deposition. Over thousands of years, streams and the ancestral Owens River had laid down this mud and clay. With no water, wind easily lofts these particles. By the latter 20th century, Owens Lake was emitting roughly 300,000 tons of particulate matter per year, mostly in dust storms. About 30 tons of this were toxic metals such as arsenic and cadmium carried on fine dust. Control measures are now in place, but the truth remains. The diversion of Owens River water caused or contributed to essentially all of that dust source by uncovering the lakebed. Meanwhile, the aqueduct itself presses on south from the Owens Valley. After the open canal past the lake, the system briefly flows into Highway Reservoir, a dammed basin that slows and stores water for a stretch of the journey. This reservoir, at a saddle between hills, was built as a buffer against interruptions upstream, for example, floods or earthquake damage. It also has an incidental benefit. As water pools in Highway, sunlight provides ultraviolet disinfection, much like natural stream exposure. In 1960, the reservoir was reworked into two smaller basins to allow better operational control. Water could be switched between the original canal and later tunnels. In fact, in 1970, Los Angeles built a second parallel aqueduct from Highway to Los Angeles to double capacity. From here southward, much of the water runs in underground concrete conduits. Burying the water is a strategy. In the hot, dry Mojave Desert, open water would otherwise lose far more to evaporation. Concrete-lined tunnels and siphons carry the flow across washes and hills. One spectacular feature occurs at Jawbone Canyon. Here the valley walls plunge, so rather than detour, the aqueduct dives 260 metres, 850 feet, and then climbs up again in an inverted siphon under high pressure. At Jawbone, gravity causes a pressure of roughly 370 pounds per square inch, about 26 bar, in the water at the lowest point. The engineers had to use very strong pipe, massive steel sections, able to handle that pressure. It was such a daunting project that the pipes were built on the east coast and shipped 14,000 kilometres, about 8,700 miles, around Cape Horn before the Panama Canal was finished. There are several such siphon sections, but Jawbone is the largest trading elevation for pressure to keep the water moving smoothly downstream. As the aqueduct flows south, it intersects other major water corridors. It passes under the California Aqueduct in the Tehachapi area. Valves and pipelines allow transfers between the two systems, giving Los Angeles some flexibility if extra water needs to be swapped. Further on, the original and second aqueduct rejoin at the Fairmont Reservoir, just before the final mountain barrier, the Sierra Pelona Range near Santa Clarita. The Pelonas could not be scaled easily, so engineers tunneled straight through. The Elizabeth Tunnel is the largest such bore, roughly 8 kilometres, about 5 miles, long, drilled through hard rock and unstable earth. It required constant support and heavy concrete lining. Once both aqueducts clear the mountains here, they operate as one system again. Flowing through the San Gabriel Mountains toward Los Angeles, the aqueduct descends steadily. Along the way, it drops through 8 hydroelectric plants, each tapping the water's gravitational energy. Water rushing through penstocks spins turbines, generating a few hundred megawatts total over the route. These plants were built to help pay for the aqueduct. At one point, the San Andreas Fault cuts the path, so engineers built the narrow Bouquet Canyon Dam above Power Plant No. 2 to provide storage and redundancy. If an earthquake broke the conduit in the fault zone, the reservoir would hold water so deliveries could continue. Finally, the water reaches the foot of the mountains. Here, 2 steep spillways, known as the Cascades, allow excess water to drop out of the conduits into the north end of the San Fernando Valley. Normally, the flow stays inside the closed pipes until it reaches underground plants in the valley. Only when flow exceeds power plant capacity does it roar over the Cascades. Once in the valley, the diverted Sierra water is treated and disinfected in Los Angeles and then stored in reservoirs for use. In the early decades, these storage lakes were outdoors, but modern drinking water rules led the city to cover them, notably with millions of floating plastic shade balls to keep light and wildlife out of the finished water. In any case, from reservoirs it is piped to taps citywide. One final oddity is that the original Owens River intake is no longer technically the first source. In 1941, Los Angeles added a tunnel from Mono Lake north of Owens to feed extra flow into the same system. This drove Mono Lake down in the same way, but environmental lawsuits eventually forced limits on that diversion. Through it all, geology and hydraulics ruled. The initial choice of Owens Valley was purely geographic. It contained a huge reservoir of mountain snowmelt, and its floor lay hundreds of meters below Los Angeles elevation. Gravity could do the work of moving water southward. The valley's geology, a porous sediment graben, made an easy path via canal to carry water alongside the river. Where the terrain got steeper, engineering inserted siphons and tunnels through rock. Every choice, from lining the canal to carving a mountain tunnel, was aimed at keeping that precious water in motion. The results were dramatic. Lakes dried, and once green meadows turned to dust when the water table fell. Owens Lake, which had existed in some form since the Pleistocene, vanished almost overnight, exposing lakeshore sediments now grey and white under the sun. Springs and wetlands, fed by aquifer levels, dropped, and the fine lake sediments became airborne dust. In hydrologic terms, Los Angeles essentially captured the entire watershed's output. The rivers now flow not to the lake, but through man-made conduit to the city, and the groundwater has been pumped down below useful levels. As the Environmental Protection Agency bluntly put it, the lakebed exposure was not natural. It was entirely the result of diverting the Owens River. By the early 21st century, Los Angeles must mitigate this dust on every square mile of former lakebed using flooding, vegetation and gravel, at a cost of hundreds of millions of dollars. Even after a century, the aqueduct still carries a significant share of Los Angeles's water, roughly 1/3 on average, and the city's growth traces back to its construction. From a purely engineering and geologic standpoint, the aqueduct worked. It linked a high snow basin to a thirsty low-lying city, exploiting natural gradients and groundwater flow. But the price was etched into the landscape. The diversion revealed the hidden costs of altering a watershed, which can be enormous. The largest flows now bypass Owens Valley entirely. The water that once kept the valley's soils green now feeds lawns and industry far away. And the dry lakebed, an unintended geologic consequence, became one of the western United States' largest sources of airborne particulate matter. This chapter in California water history is thus as much about rocks and water as about human ambition. It shows how geology, mountain building, sediment deposition and valley formation created a pathway for engineers to reach hundreds of miles of new water. It also shows how disrupting those natural flows can turn an entire lake into a dust bowl. For science enthusiasts, the Owens Valley to Los Angeles aqueduct system is a cautionary tale of hydrogeology, a grand example of engineering meeting geology and of nature rearranging itself when the flow of a river is changed.